Go ahead.
Okay, so thank you very much. I'll start with a very brief recap of yesterday's lecture, and then I'll pause for questions. So yesterday we saw that black hole thermodynamics is situated very nicely in the context of quantum gravity in AdS5 space, AdS space. And the way we do quantum gravity in AdS space is that you have some conformal boundary where you fix the boundary conditions for all the bulk fields, the metric, the gauge field, and whatever else is there in gravity. And then in the interior, you're supposed to let all these fields fluctuate. And then you do a path integral over these fields, over these fluctuations. Okay? So that's how we understand quantum gravity in AdS. And this naturally leads to the canonical ensemble in the thermodynamics. Okay? And the boundary values of the supergravity, of the gravity fields, are directly equal to the chemical potentials for the various fields. So for instance, the temperature is just the radius of the circle, the G55 GRR component, sorry, G55 TTT component, excuse me, and so on. Okay, and then we saw in detail how all these things come about. Maybe I should call this grand canonical ensemble. Yeah, okay. All I mean is that all the chemical potentials are fixed and charges fluctuate. Okay. Then we saw that the gravitational partition function has the following expansion. So we don't know how to really do quantum gravity, but at weak coupling, when G Newton is small, or in the dual theory when n is large, then we can do an asymptotic expansion. So you write the full partition function as a sum over saddles of e to the minus the action, and this action is some quantum effective action with corrections in 1 over n. So today and in the rest of the lecture, these actions will only calculate at large n. Okay, so this is the leading classical action. Then we saw that there are two saddles, AdS5 and the AdS5 black hole. By black hole, I always mean the black hole in AdS5. And then we focused on the supersymmetric black hole. So the context here was minimal supergravity or 8 supercharges. The solution had 3 charges, 2 angular momenta and 1 electric charge. The supergravity, minimal supergravity, has 1 gauge field. This is gauge supergravity. And the chemical potentials dual to these charges are called small omega 1, omega 2, 5. So what we saw yesterday was that if you calculate the naive chemical potentials according to Gibbons and Hawking, then there's some issue there, and then we discussed how to resolve that. And then instead, we're supposed to define these chemical potentials as limits towards the extremal supersymmetric black hole. And in doing so, naturally, these things are complex. Okay? And in particular, they obey this constraint so that the linear combination equals 2 pi I. Okay? So they have to be complex. Then we saw that the action of the black hole doesn't depend on the temperature anymore, as we expect, and it's equal to this function, and this function will come up again and again. And the way I remember it is that it's a function of chemical potentials, and it's just a cubic divided by a quadratic. Okay, so this will come up again. Okay, and then we also saw how to think about this constraint in a slightly more geometric way. That in the Euclidean theory, you have this cigar-like solution. This is the black hole, Euclidean black hole. And here's the horizon. And smoothness at the tip means that the killing spinors are anti-periodic. So there's a momentum, half integer value of momentum at infinity. But as we all know from basic quantum mechanics, momentum is not a gauge invariant concept. So it's actually the momentum plus the value of the gauge potential. And the gauge potential is exactly tuned so as to sort of cancel that value of momentum so that you actually get a killing spinor. Okay, so you have supersymmetry. Then the final thing we saw was that this on-shell action of the gravitational of the black hole, the AdS black hole, acts exactly like the free energy. So it is in the sense of Gibbons and Hawking that the entropy is a Legendre transform of this on-shell action when there is this constraint. Okay, so this was a small recap. Any questions so far before I move on? So some of you asked some questions on Slack, but anything else? Okay. So now today we want to move to the boundary theory. Okay. So the first question is, what exactly are you calculating in the boundary theory? Okay. So we saw, so in the general thermodynamic framework, you have this S3 times S1. So this is the thermal circle. But that was in the case, that was in the simplest case where you're considering Schwarzschild black holes, okay, where the only parameter, only charge was the mass, and dual to that was the temperature. Now we also have angular momentum, okay, and electric field. And so we should consider some gauge field. And also in the metric, you'll see that there are these off-diagonal terms. Okay, that's because the rotation of the black hole. As we saw, these are precisely the chemical potentials for angular momentum, J1 and J2. Okay, so these are the capital omega 1 and omega 2, okay, a la Gibbons and Hawking. Okay, so there are these mixing terms. In other words, there's a twisting of the S1 over the S3. Okay, and now the point is that the fact that the bulk is supersymmetric and there's a killing spinner just automatically implies that if you just take the boundary value and go to start with the 5-dimensional supersymmetric background and go to the 4-dimensional boundary, then you automatically get a 4-dimensional supersymmetric background, a 4-dimensional supergravity background. Okay, just as the limit of the 5-dimensional supergravity. And this 4-dimensional supergravity should be thought of as something which is not fluctuating, you fix it at the boundary, but which allows you to put a supersymmetric field theory on that boundary. Okay, that's how we think of supersymmetric field theories in curved spaces. It's a solution of, offshore solution of some supersymmetric theory of gravity. Okay, that's one way to understand it. And because the bulk functional integral was manifestly supersymmetric, we made sure of this. What we are calculating in the boundary is also manifestly supersymmetric, and you just get the supersymmetric partition function. Okay? So that's one way of understanding what you're calculating in the boundary. And by this, I just mean an integral, a path integral with supersymmetry. Okay? Now, of course, there was something a little bit subtle about this periodicity and the gauge field and so on. So it's worth understanding this, if this was a bit too slick, a little more in detail in the Hamiltonian version. So let's do that. So I'm going to call omega 2 pi I sigma, omega 1, and omega 2 2 pi I tau for the rest of the talks now. Okay. And the constraint that I wrote can be rewritten as follows. Phi is pi I times sigma plus tau plus 1. So now let's write the boundary partition function. So in the boundary, it's a field theory. I'm not saying what it is at the moment. There's some Hilbert space, but it's a field theory. So we have a notion of a thermal trace. So we do that. We write a trace, okay? And you only put the potentials that are there, that are given to you, okay? So first, you just put, first let's just do it naively where again, the fermions are antiperiodic. You just get trace of the e to the minus beta Hamiltonian. There's a potential for J1, for J2, and for the R charge. And now what I'm going to do is to solve, plug this in, okay, and solve for phi. It's a completely linear constraint. It's completely trivial to solve. You do that, and what you get is this. You get here, there are 3 terms here. One of them goes into sigma, one of them goes into tau, one of them stays as such, k to the pi I r. All right. Now, what I do is you observe that by the spin statistics relation, okay, e minus 1 to the f is equal to e to the 2 pi I j1. Okay, j1 is one of the angular momenta. I could have chosen j2. This is just spin statistics. Yeah. Okay, so fermions have half integer spin and bosons have integer spin. So I put this 1 over here, and what happens? So what I get is that there's a minus 1 to the f, okay, because of this. There's e to the minus beta times Hamiltonian. And now this extra term combines with this term, and I get precisely, so there's one term from J1 and one term for R. So the net effect is that you get a minus 1 to the f, and then this chemical potential sigma shifts by 1, and that's it. Okay, so you see naturally that even from the Hamiltonian perspective, you get a supersymmetric partition function. It's traced -1 to the f of something. Okay, just follow your nose, and that's exactly what you get. And for most of you, many of you will recognize that this is precisely the superconformal index of n equal to 1 superconform field theory on S3 times S1. Okay. Now, again, I know many of you are students, so maybe this statement is not obvious. And in fact, I decided to spend the whole lecture on just explaining this statement. Okay, so it's all going to be field theory. I'll just tell you, I'll start now from n equal to 1 superconformal field theory and explain what is the superconformal index and why it has this form. Okay, so that's the plan for today's lecture. Okay? Any questions before I begin? So everything I will say from now on today will be completely a review. Okay, the things I said here is, yeah, so sorry, I've been a little bit slack with references. So this is in the paper with Cabo Bisset, Cassani, Martelli, and myself in 2018. Okay, so all of this is from there. And actually throughout the lectures, I kind of consciously decided to be a little bit slack with references. And the reason is that it just sort of clutters up the slide too much, but that's also not quite correct. So what I'll do is I'll put up on Slack just one page, maybe tonight or tomorrow, with all the references. Okay.
Could I quickly ask, can you remind us what is R? Is R the radius of S1 or?
No, not at all. So let me remind you, here it is. So let me go here. Remember that the context is minimal supergravity. So you have Einstein-Maxwell theory in AdS space. Okay, so it's gauge supergravity. Einstein-Maxwell means that, so the Einstein pair has 2 rotation charges, and the Maxwell means that's 1 U1 gauge field, which I'm going to call R. Oftentimes it's called Q. In fact, in this 2018 paper, we call it Q. It's just the electric charge with some electrostatic potential. Okay. The radius of, thank you for asking, the radius of the circle is called beta, and that completely decouples from the problem that we saw yesterday. Any other questions?
Okay, thanks.
And you'll see today why this is called R, why I chose this. Okay, okay. So then let me begin with really the basics. So this is both a toy model, but in fact, this is the real thing, as you will see. Okay, so it's good to start here. So let's start not with superconformal field theory, but just supersymmetric quantum mechanics. Okay. So I treat this as a review, but also to set up notation and so on, okay, and the ideas. That's my general theme. So I consider any supersymmetric quantum mechanics with one complex supercharge, QQ bar, with this algebra. QQ bar anticommutator is the Hamiltonian. All right. And now, oops, notice that, sorry, so the algebra is that QQ bar is H, and H commutes with both Q and Q bar, Q dagger. Q square is 0, Q dagger square is 0. Anything that I don't write is 0. And now notice the fact that this is Q and Q bar, Q dagger, means that the Hamiltonian is non-negative definite. Okay. That means that the energy can either be 0 or positive. Okay, so unlike usual quantum mechanics, the 0 has a meaning in supersymmetry. And now, what are the representations of this algebra? Okay, when E, the eigenvalue of H is positive, then you just divide this equation by E, and you'll get some oscillator, let's call it chi, which is chi dagger equals 1. So that's just one simple Clifford algebra, and the representations are 2-dimensional. So let's call it psi and Q dagger psi. So in this way, you go by, sorry, maybe I should say this. So this way, what happened? Q dagger, another Q dagger gives 0. This way is Q, and another Q. Sorry, my iPad is behaving strangely. There you go, another Q goes 0. Okay, so the standard Clifford algebra is 2-dimensional. And when E is 0, then that means that both Q and Q dagger annihilate the state, and therefore you only have a 1-dimensional representation. Okay, so here it is. So these are called long multiplets or non-BPS multiplets. These are short multiplets. Okay, here is the picture. So the long multiplets always come in pairs. So you can check that these two have the same value of energy. That's because of this. And this one has 0 energy. Very good. Okay, let's go on. So now we go to the famous Witten index defined by Witten, which is the following. So it's the trace over the Hilbert space of -1 to the fermion number times e to the minus beta times Hamiltonian. Okay, fermion number, of course, is +1 for bosons, -1 for fermions. And this is a very simple definition, but it's a very, very beautiful and powerful construction. Let's go through it, its properties. So firstly, notice that it's going to be a trace over everything for any non-BPS or massive representation. Because they only come in pairs, they're going to cancel because of the -1 to the f, and so they won't contribute, and therefore the answer is independent of beta. Whenever h is positive, there is no contribution. So the answer, so the whole trace collapses to the 0 modes, to the 0 energy sector, and in the 0 energy sector, it's just trace is the number of bosons minus number of fermions. This is also called the index of the supercharge. This is index in the sense of the Dirac index or mathematical indices. Okay, so the whole thing can be thought of as a trace over BPS states, but it's important in the definition that you have the e to the minus beta h, because this gives you a regulator. This can be defined as a trace over the full Hilbert space, and this regulates the high energy modes. The fact that it is defined as a trace over the full Hilbert space means that it can be written as a path integral. Okay, this is the usual rules of quantum mechanics, the Feynman rules, the Feynman understanding of the path integral. And the only difference when you work through that to go from Hamiltonian to path integral is the fact that the fermions and bosons are periodic around the time circle. I meant, of course, this is the Euclidean time circle. Okay. Now, the fact that that z is independent of beta also means that if you change the Hamiltonian in a supersymmetric manner, then what happens? Then the spectrum will shift up or down. Each of them will sort of go up a little bit, go down a little bit, something like that. And in fact, 0 energy states can also lift off. But because of the algebra, the movement will only happen in pairs. Okay? So any massive state will always be still paired, and therefore the actual the value of the trace at 0 energy will not change. If there's any lifting off of 0 energy states or coming down, they always happen in pairs, so it's not going to affect the index. But therefore, the index is invariant under the deformations of the Hamiltonian. Sorry, I have a feeling I'm going too slow. I'm also lecturing at King's at the same time, so I'm mixing up the level a little bit. So I'm going to speed up a bit. Sorry about that. Okay, so that's the Witten index. So any questions about that?
By the way, just a comment. I don't think you are too slow. I think you are at the appropriate pace.
Okay, thanks. Okay. Yeah. Good. Okay, so now let's go on. So now what we do is you take this Witten index and you dress it up. Okay. So in addition to this, trace minus 1 to the f, now you can add any operators of this form, and everything that I said so far will still hold true, will still hold, as long as these operators also commute with the supercharge. In effect, you can think of this as deformations, supersymmetric deformations of the Hamiltonian. Okay, so as long as these operators commute with the Hamiltonian, everything I said is still true. Okay, but we now think of this as follows: that this mu. So now the Witten index depends a priori on beta and mu, but it doesn't depend on beta for the reason I said. Now it depends on mu, and the role of mu is twofold. Okay? So firstly, it refines the index in the sense that the Witten index, as beautiful as it is, at the end of the day gives you a number. Okay, given any theory, the Witten index is 3 or 4 or n or something like this. That's also very non-trivial information. But we want more information. So even on this set of 0 energy states, we try to sort of put more information about the quantum numbers, and the thing you can do is to do it for the supersymmetric operators. Okay, so in that sense, it refines it. It also regulates it because oftentimes, especially when we go to field theory, the state of BPS, the space of BPS states itself many times is infinite dimensional. And therefore, let's say you have an infinite number of bosons, that trace is also not well defined. And this serves to regulate that trace. Okay, so it plays this dual role. Now, everything I said until here applies. So I said it for supersymmetric quantum mechanics, but it applies equally well to superconformal field theory, supersymmetric quantum field theory. Okay. When you think of supersymmetric quantum field theories in infinite space-times, then there are subtleties. Okay, there are subtleties because sometimes there can be a continuum of modes, and here in all these arguments, as Witten did, I assumed a discrete spectrum because otherwise the trace itself is not well defined. You have to worry about such things, and those cause subtleties. If you have a continuum, for instance, this is no longer true. Okay, there are all these things. Nothing of this will affect us in these lectures. And one reason to avoid it, and in fact that's natural for us, is to place the supersymmetric quantum field theory on a compact space. Okay. Similarly, there are no boundaries. So think of some sphere. In effect, what you're dealing with is some infinite dimensional quantum mechanics. Okay, so everything I do really goes to. All right. Okay, so now I'm going to then go to n equal to 1 superconformal field theory, unless there are questions. Okay. So the n equal to 1 superconformal algebra is, so the bosonic sector is the conformal algebra. So this is in 4 dimensions, so it's SO4, 2. So that's the same as SU 2, 2 at the level of algebra. And it's n equal to 1 CFT, which means that there's a /1. This is the super algebra. A /1 means there's a minimal 4-component spinor. This SU2, 2, there's an SU2 times SU2 embedded in that. I'll call it SU2 and SU2 tilde with Cartan elements J and J tilde. Okay, this is the same as we saw, of course, as we saw in the AdS space yesterday, and these are the same notations, J and J tilde. There is this supersymmetric Hamiltonian with energy with eigenvalue E and the U1, and there is a U1 R charge in the algebra. I haven't written down the algebra, but I assume everyone at least has seen it sometime. There's a U1 R charge in the algebra. That's why I call this R. Now here are the spinors. So this is the basic supersymmetry, Q and Q tilde, which rotate in the left and right SU2s. And then because it's superconformal, there are conformal supercharges, which are S and S tilde, which actually happen to be the conjugates, Hermitian conjugates of Q and Q tilde. Okay, so Q and S are in the left moving SU2, and Q tilde and S tilde are in the right moving SU2. And the R symmetry, the conventions are that R and Q commutator is minus Q, R Q tilde is plus Q tilde, and when I look at a dagger, I should make a plus here. Okay. And then here is the basic algebra. The algebra is that Q dagger commutator, anti-commutator is E plus 3/2 R when alpha and beta are the same, and when alpha and beta are not the same, this J enters the story. Okay. Similarly, there's a right moving algebra. Okay, so this is the full superconformal algebra. And what we need for our story actually is what we're going to do, the superconformal index is actually just a Witten index. So that's the sense in which I said that is the thing, in the sense that you just pick one of these supercharges and write the Witten index for that. And that's called the superconformal index. Okay, Witten index dressed up in the sense that I told you. So I pick this, you can check the algebra. And what you get is this algebra. So now you get an algebra of one complex supercharge, Q dagger anti-commutator is E minus 3/2 R minus 2 J naught tilde. Okay, and E and Q is half Q, and J naught tilde and Q is minus half Q. Okay, if you sort of don't like this kind of superconformal algebras, you can just begin with this simple algebra of just one complex supercharge. And trust me that I've done my calculations correctly, but I urge all the students to verify all this. So this is the algebra we'll be working with. Okay, now we want to write the index, and we want to write the most general index. Okay, we want to dress it up as much as possible, get as much information as possible. Okay, so what we do, so in order to do that, remember that I had here, I had a trace -1 to the f e to the minus beta h, and here I was supposed to put supersymmetric operators. And now my goal is to put operators that don't depend on the theory, only depends on the symmetry algebra. And therefore I should look for operators that commute with Q inside the algebra. Okay, that's my goal. I want to get the most general index which applies in the most general setting. That's the idea. Okay, and if you do that, you'll see that the commutant of Q has rank 2. Okay, there's no so there's one supercharge that goes away. So it's a bosonic SU2, 1, and there are 2 generators, and we can pick that as follows. So look at this algebra here. So E plus J tilde naught commute with Q, because this is plus and this is minus. So you take E plus J tilde naught. Sorry, my conventions, I should have said, if it's not clear, here it is. My SU2 conventions is that the J vector is J plus minus and J naught. So J naught means the curtain of that. E plus J tilde naught. And because this is purely right moving, everything here is right moving. Okay, the left moving J commutes with it. So I pick J naught. Okay, this is again a convention. It's often used in the literature. So these are my 2 generators. Now, remember that the trace collapses to the trace over BPS states, and on the BPS states, the right-hand side of supersymmetry commutator is 0. So E is 3/2 R plus 2J2. You plug that here. What you get is the 2 generators are R over 2 plus J naught tilde plus or minus J naught, which I will write as, so this is exactly J1 and J2 in the usual notation. So J1 plus ½ R and J2 plus ½ R. Okay. And therefore, the most general index is as follows. It's trace of -1 to the f e to the minus beta times the Hamiltonian times some chemical potential sigma coupling to J1 plus ½ R, some chemical potential tau coupling to J2 plus ½ R. Okay, so that's where I wanted to reach. And are there questions before moving? And this, what I wanted to say was, this is, so I should maybe mark this. Before this, let me say one thing. That this is, of course, in addition, this is only the most general algebra within the n equal to 1 algebra. If I have other things, I can always introduce other operators, which I'll call flavor. Okay, which means that it commutes with supersymmetry. Okay, I can of course always put in any flavor generators that I want. All right, and this here is the most general super conformal index. Okay, let me see if I can hold my hand steady. There we go. Okay, and indeed for n equal to 4 super Yang-Mills, the most general index even within the algebra is bigger because it has more generators. There's an SU4 R symmetry that has 3 Cartan generators, R1, R2, R3. And in the language that I set up for n equal to 1, you break these SU4R to U1R plus times flavors. And one combination of this is our R, and the other 2 combinations are some flavors. Okay, so you can also do this. I won't even sort of explicitly write this. I'll just stick to this. Okay, so
I have a question.
Please.
So when you were computing the commutant, you could have taken a linear combination between the dilatation and the spin as well, right?
Here, that's it. E is the supersymmetric Hamiltonian. So it's the right-hand side. So sometimes you can call it delta. Yeah, I just call it E because I call it H. Yeah.
Okay. All right. I see. Yeah. Okay. Yeah.
Sorry.
Okay,
here it is. Yeah. So this, sometimes people call this delta. So it was E in my Witten index calculation. When it's conformal, this becomes delta.
Okay. All right. Yeah.
It's energy in the radial quantization. Other questions? Thanks, Subramanya. Okay, then Let me count till 5. Okay, so then the next part of the second half of today's lecture is how to calculate this. So I said, as I said, I have not given any references, but maybe I'll just scribble something here, because I should say that all of this, and I'll write this more carefully later. There's a very beautiful paper. Okay, by Rommersberger. I think it's in 04, if I'm not mistaken. And then Kinney, Maldacena, Minwala, and Raju, also in 04. Okay, and then Christian Rommersberger actually sort of developed these things very nicely, and there are other very useful references. Maybe I should say that. For those of you who are more mathematically minded, there's a good reference by Spiridonov and Vartanov. Okay, oops. Okay, I can't do that either. I don't know what Siri thought. Okay. Yeah, so as I said, I'll give you more references, but these are the basic references on which where you can find all this. All right. Okay, but my aim is also sort of to give you enough information in the lectures that you can actually just calculate everything. So let me move on. So the next topic is, how do we actually calculate it? Given a theory, how do we calculate it? And I would like to calculate this for some broad class of theories. So general n equal to 1 superconfirmed field theory with with some matter content, so some vector multiplets and chiral multiplets. Okay, I'll keep as an example in mind the n equal to 4 super Young-Mills whenever I need to write equations. Everything is general. Okay, so the starting point is the state operator correspondence for conformal field theories. Okay, the fact that that every state in a superconformed field theory is mapped to local operators is very useful, because that means that what we have to do is to, when we want to calculate this trace, is to enumerate local physical supersymmetric operators. PPS is shorthand for supersymmetric. Okay, and compare, this is just, I make this comment, so compare this with like other supersymmetric indices. When you don't have conformal invariance, sometimes it's a much more complicated problem. There might be non-local operators, there might be background flux, all kinds of things. So for a superconformed field theory, it becomes particularly simple. Okay, and you can choose to enumerate this operator at any chosen point, let's say the origin. All right. Now, suppose, as we will have throughout these lectures, that the conformal field theories in question have a Lagrangian description. Okay, so there's some coupling constant in the Hamiltonian, in the Lagrangian. And from what I said about the index does not depend on the value of this coupling, and therefore you can actually tune it to be 0, and therefore calculate at the free point. Okay, so all you need to know is the representations. You have some fields, you just ask how do they fall into reps of the algebra, and then just write out the trace. Okay, and for the same reason that there is no coupling constant, you can actually treat each multiplet separately, because there's no coupling. Okay, so it's particularly simple. Okay, so how do we do this? Well, so the problem then becomes the following. You take all the fields of the theory, and all you have to do is treat them as free fields and write what are the BPS gauge invariant words. Words just means any string of operators. Okay, and you don't have to worry about anything like renormalization, coupling, dependence, anything like that. It's a very simple problem, and it's a combinatorial problem. Okay, so the idea is this. So you first think of all the fields in your theory, and with derivatives acting on them as letters. So these you call single letters. Then from the single letters, you form words. So this is one word, phi squared, d mu phi psi. Okay, then you impose gauge invariance and supersymmetry. that gives you the space of states on which you're supposed to count this trace, and just then for you write, make a list, write the charges minus 1 to the f, and sigma, so j1 plus r by 2, j2 plus r by 2. Okay, that's all you have to do. All right. So the question now is there a sort of simple way, smart way to enumerate these words given some theory? Okay, so this is some combinatorial problem, and I'll work through this with a set of examples. Okay, I won't give you general theory. There's a whole general theory in the whole field of mathematics which studies this. So let's just take some simple examples. So first, as a first example, forget about supersymmetry. Just take a quantum mechanics of one variable phi. Okay, imagine it's not a field but a quantum mechanical variable, and calculate trace of x to the energy. Suppose there's only one charge, which is the energy, and x is some chemical potential. Okay, the way to do it is the following. So I'll give you an algorithm, and then you will see that it works. Okay, that's my method. So you first write the space of all single letters. Okay, in this case it's quantum mechanics, and there's only one field, so there's no derivatives, no fermions, nothing. So therefore, the only single letter is phi itself. From this, you form what is called the single letter partition function. So that means, by definition, it's trace of x to the e on this Hilbert space. Okay, in this case, it's particularly simple. It's just x, and this we'll call small z of x. This s means single. Right? Then you look at the space of words. So the words here are also simple because there's no derivatives, nothing. So it's just 1, 5, 5 squared, etc. And now what we want to calculate is this trace e of trace x to the e, and this is I'll call capital Z, and it's just 1 plus x squared, etc., which can be summed formally to 1 over 1 minus x. Okay, so I just wanted to, so I've not done very much. I've just shown you that there is something called a single letter trace and a word trace over words. And the single letter trace is simple x, and the trace over words is just 1 over 1 minus x. Let's repeat the exercise for two fields, phi1 and phi2. Okay, in this case, suppose they both have energy 1. So the single letter Hilbert space is just phi1 and phi2. Okay, and therefore the single letter partition function is just x plus x, which is 2x. And now, what are the words? The words are, you can have nothing, you can have phi1 squared, etc., or phi2 squared, etc., or phi1, phi2. But they're free, they're not talking to each other. So as far as enumeration is concerned, the answer is just 1 over 1 minus x for phi1 and 1 over 1 minus x for phi2. It's just 1 over 1 minus x squared. Okay. So I think you all see the pattern. The pattern is always as follows. You write the single letter trace, call it small z, and it's some sum of this type, sum an x to the n. Okay, this can be finite or infinite. In this case, in these examples, these were finite. And the answer, the trace over words, is product. Okay, for every n, there is 1 over x to the n. Okay, this n is the energy. So 1 over 1 minus x to the n. Okay, and if I have a degeneracy here, it becomes a degeneracy in the product. All right. So any questions so far? All right, so we're just doing some combinatorics. So now notice, if you stare at this, so I'm going to take a log of this. Okay, so log of z is minus a sum over n, an log of 1 minus x to the n. All right, now I'm going to expand the log as sum k 1 over k an x to the nk. Then, because it's all formal manipulations that I'm doing, I'm just going to interchange the order of summations. What I get is 1 over k times sum n an x to the kn, but this is nothing but z, small z, of x to the n. Oops, x to the k, I meant. Right, okay, look at this. And therefore, we find the map that we want to go from the single letter trace to the single word, to the full word trace. Okay, and the map is as follows. Log of Z is what is this object? It's 1 over k, sorry, it's this object, 1 over k Z of x to the k, which I wrote here, and therefore Z is just exponential of that. Okay. So you can give a more formal proof of this, but it's just this simple combinatorics, and this has a name. This operation, which takes you from the single letter trace to the full word trace, multi-word trace, is called the platistic exponential. Okay. All right, nothing mysterious about it, and we're going to use this. Maybe I'm unbox it. Okay. Sometimes people call this the multi-particling formula, okay, for obvious reasons. Okay, now an exercise for you is that everything I said actually works not just for the simple trace of x to the energy, but for any type of refined trace. You can have any operators, you can have -1 to the f, everything I said goes through, in the sense that you start with the single letter object here. Okay, sorry, I should have put an S here. Start with the single letter object, and then you get the multi-word trace with this formula. Okay. Okay, now we go to gauge theory, which is where we want to go. So far we understood the following. So the first thing to do is to just construct this single letter trace and separately for each multiplet, like I said. Now, for gauge theories, there is one other subtlety, namely that, so what we want to do is you start with single letters, you form words, and you want to enumerate these words, and you want BPS operators. So far we've done that. BPS just comes automatically from the trace -1 to the f. But there's this other issue of gauge invariance. And in order to do that, there's one more trick, which is as follows. So in the single letter trace, what you do is you keep track of the gauge charge as well. Okay, so you define your single letter index as the usual index, trace -1 to the f, what we defined earlier. But include here, I should say what this is. This is the character the character of the gauge representation. Okay, so you include that. Okay, this is the algorithm, and you'll see why it works in a second. Okay, so this single letter trace now depends on a matrix U, which is an element of the gauge group. I'm just going to keep UN for simplicity, and this is the character that you want. Okay, so first you calculate this. Then you do the same thing as before. You multiply different multiplets. You put, because these are all free fields anyway, you multiply all the different single things. You take the platistic exponential. Sorry, yeah. Okay, it should be in the other order. Excuse me. I mean, otherwise you have to take the sum first, and then you first do platistic exponential, multiply different multiplets as before, and then here is the final thing. You have to project onto gauge singlets. So what you did here, you just kept track of the gauge charges, okay? But a generic element in this trace will have gauge charge. It's not a gauge invariant object. And if you want a gauge invariant object, what you do is after putting together all these multi-words and multi-particles, you just project onto the singlet sector. That you can do by just integrating over du. It's like the zeroth Fourier component. Okay, you have some, or if you want to take an average over the gauge group, that's another way of saying. Okay, so that's all it is. So this is the formula. Okay. Okay. And there's one more subtlety, namely that in field theory, so we said that when you can do this multi-particling trick when the operators are all independent, but in quantum mechanics examples that I showed you, the operators were already independent. In field theory, there's an issue that because you have derivatives, you can have an equation of motion. So the operators for instance, box of phi is not independent, it's 0. And therefore you have to subtract it. So the best way to do it is actually, again, another trick, namely you just think of the equation of motion itself as an operator and subtract it when it appears in the trace. Okay. So now we're going to apply this to the n equal to 1.
Can I ask a question?
Yes, please.
Can you explain how BPS is automatic? Is it obvious that if single letter operators are like BPS, then the products will also be BPS? Is that obvious?
Thank you very much. That's a fantastic question, and that's hopefully you will tell me. You will verify this by tomorrow. That's exactly this exercise. Okay. So I'll just tell you again what the statement of the exercise is, that if you start with any index, okay, of this sort, okay, which projects onto, let's say, half BPS or 1/4 BPS or 1/8 BPS states, and do this platistic exponential, then you get here the same index on the multi-word Hilbert space. That's the exercise. And therefore, you're guaranteed to get the same BPS states. Yeah? So if you're saying something, you're muted.
Well, here you're just saying that if I add some chemical potentials to the trace.
Well, and a -1 to the F, crucially.
Right.
That's the thing that projects you onto BPS states.
Okay, yeah, right. That's right, yeah. Thanks.
Okay, other questions? Okay. Okay, in that case, oops. Alba, I have what, about 15 minutes, right?
Yeah, you have 10 minutes or something.
Okay.
15, but just take your time, don't worry.
Okay. No, I put a stopwatch because sometimes I tend to ramble, so. Okay. Okay, so now our goal is to calculate this index that we want. This is the most general index that we want to write down. And here I've changed notation to, so e to the 2 pi sigma I'll call P, e to the 2 pi tau I'll call Q. Okay, so this is our goal. We want to calculate this for a general class of theories with n equal to 1 superconformal symmetry. So the first goal is to write to calculate the single letter index. Okay, so here I've done that. Okay, I did this on Monday. So you make this table. You just list all the single letters. Okay. I didn't finish it because I knew the answer. I've done this many times. This is an exercise for all the students. This is really instructive. What you do, you list all the single letters. Here you write all the charges. So this is the right-hand side of QQ dagger commutator. Okay. So when you're picking up trace of -1 to the F, you know that it only picks up fields or states when this vanishes. Okay. So you write all the charges and ask, there's a finite number of these things. There's phi, phi star, psi, psi minus, and that's it, I think. Yeah, that's it. Okay. Psi dagger, plus and minus. And then you sum this up and ask which one becomes 0. Okay. These ones are not 0, I checked. The ones I didn't write. And the ones which are 0, you pick up. So there's that. There's that. And similarly, as I said, you have to write this equation of motion as an operator. In this case, actually, you find that it's never 0. Okay, so this is not equal to 0. So this is also not equal to 0. And finally, here for field theory, remember that there are also derivatives. Okay, and actually, there's an infinite. Remember that in field theory, there's an infinite number of single letters in the way I defined it. There's phi, d phi, d square phi, etc., etc. But one trick is that you can think of the derivative itself as an element, and because it's free apart from the equation of motion, you can just basically what's happening is it's the free ring generated by these and these modulo this relation. Okay, that's exactly what's happening. Okay, so what you can do is just list the charges of the derivative itself. Okay, and ask which one becomes 0. And it turns out that of the 4 derivatives, so here this is not 0, these two are not 0, and these two are 0. So of the 4 derivatives, there are 2 derivatives. So here I've chosen light cone notation, plus and minus. So this is the SU2 times SU2 tilde notation. Okay, so 2 of them are 0 and 2 of them are not 0. And now you'll see how I map this. So, and then what you do is you, for every such, wherever you find a BPS state, you ask, what is the PQ power of that? Okay, for that you need J3 plus half R, which is 1/3, and J3 tilde plus half R, which is 1/3. Okay, and so on. All right. So here you get that. So what you get is something like this. You get this thing from here, then you get a minus PQ to the 2/3 from here. Okay. And then the derivatives, there is a P and a Q coming from these 2 derivatives. And the fact that the derivative can act arbitrary number of times means that it's an infinite series that goes in the denominator. Okay. So the single letter index itself is an infinite series. Then you have this chi adjoint. Very good. And similarly for the vector multiplet. So this is also an exercise. I didn't do this. Exercise. Okay, so just finish all the tables, write a table for the vector multiplet and verify this is the case. I've already gone to adjoint because I'm looking for Yang-Mills. Let's say I'm looking for n equal to 4 super Yang-Mills. So what is the adjoint character? For UN, it's just trace U dagger. So if I write U, if I diagonalize U, then I'll get a sum of, so the eigenvalues, remember U is unitary. So the eigenvalues look like e to the 2 pi I U1. I didn't say what is small e. E here. My notation is E of x is e to the 2 pi I x. Okay, throughout the lectures I'll use this. Okay, I borrowed this from the mathematicians. It's a very useful notation. So what you have is the eigenvalues are just phases, pure phases, okay? And these phases I'll call small u1 up to small u1, the angles, e to the I u1, etc. So these ui's are defined between 0 and 1, okay? And what you get then, so I just made this completely explicit, and what you get is this formula for the index, okay? More generally, you will see that this thing here, sorry about that. More generally, this here is a sum over the representations of that. Okay, it's the sum. So take the representation. You have sum over all the weights, and you get that. Okay, rho in R means those are the weights. Okay. Anyway, if you want to be explicit, let's just do that for the adjoint. It's completely explicit. Very good. Okay, good. So I have about well, I have 7 minutes on my clock, but I have about 10 more minutes. So I'll try to do it. Okay. So any questions about that before I go
on? To what extent does imposing gauge invariance by integrating over the group true for the partition function? Is it true for the quantum mechanics partition function?
It's true very generally. So any gauge system is true. So the first examples I showed you, the example 1 and 2,
yeah,
there was no gauge invariance. I just said take a quantum mechanics of one variable with there's no gauge field at all.
Right.
If there were a gauge field, I would have had to also integrate over the gauge group there. Okay. Yeah.
I'm talking about not for the index, but for the actual partition function.
Yeah. That's all. It's still true.
It's still true.
Yeah.
Oh,
yeah.
Okay.
Okay.
So you would just get rid of
minus 1
to the f. That's
exactly.
That's it.
Okay. Of course, there that object. So the thing that you just described is the partition function of the free theory. Okay,
I see.
the free gauge theory. What we're calculating is the supersymmetric index of the free gauge theory, which is also equal to the supersymmetric index of the gauge theory. You can just remove the word free because it's an index. While for the partition function, you can't do that. If you want to calculate the partition function for the full gauge theory, the best you can do is turn on couplings, and then you have to worry about quantum corrections, mixing, all those things. People have done that.
I see. Thank you.
Yeah. Other questions? I should, on that point, I should say, for the actual partition function, sometimes it happens that when you switch on a gauge coupling a little bit, go between 0 and 0.1, sometimes it happens that there's a dramatic change in the partition function. So 0 coupling, the free field partition function, tends to be a bit degenerate, and sometimes you see many more states, for instance, than is actually present in the theory. Okay, the index, this does not happen. Any cancellations that had to happen already happen at the free point. Okay, so that's an important point. Thanks for the question.
Thank you.
Okay. Okay, so in the last 10 minutes, what I'll do, I want, so I have this expression now where I got the index as an integral over unitary matrices. And now I also want a very explicit expression if you want to, for instance, put it on the computer. Okay, you can also do it there. I'm just going to rework it. So recall that this platistic exponential is like this. It takes a sum of this form to an infinite product. And I want to explicitly write out these infinite products for the gauge theories. Okay? So here's a single letter partition index for the chiral multiplet. So you ask, what is the platistic exponential? So this is an infinite series. You just expand 1 minus p, 1 minus q, get infinite series. So you get an infinite product. So this is the infinite product, which is defined as follows. Okay, here it is. Okay, there are numerators and denominators coming from the fact. So the denominator is sort of encoding. You can think of this. I won't say more. So just work this out. You will see. Just write this as an infinite product, infinite sum, and check that the platistic exponential, according to this rule, gives you this infinite product. Okay, so it's an algebraic exercise. This product over ij, the sort of eigenphases, comes from the fact that you have this character. This function has a name. It's called the elliptic gamma function. Okay? It's been studied by mathematicians. And we'll pick up on this tomorrow. So that's for the chiral multiplet. Okay, so the chiral multiplet can be written very nicely in terms of known functions which have interesting symmetry properties. What about the vector multiplet? But before that, I want to discuss the measure. So there's also a measure factor, remember? So this invariant measure, you want the invariant measure over the gauge group, the Haar measure. And this is a standard formula. You find that it can be written as an integral over these eigenphases, okay, with some van der Mondel type determinant. Okay, so it's in e to the 2 pi I. Okay, so that's a standard formula. Remember, this integral essentially goes from 0 to 1. So it's over the circle of the unitary matrix. Okay, this is for UN. For SUN, you'll have constraint of this type. SON, SPN. Please work out it. So there's an exercise. So exercise to remind yourself. It's all fairly standard. I don't know what's happening. Sorry about that. Okay. For the vector multiplet, it turns out that this platistic exponential itself does not give a nice function, but combined with the measure, it actually gives exactly the same function. Okay. So the measure plus the vector multiplet somehow acts like as if it's a chiral multiplet of R charge 2. So remember that the free chiral multiplet, I said this very, very quickly, but it's worth saying that the R charge of the free chiral multiplet is 2/3. I've already used that. Okay, so that's this 1/3 and 2/3 that you see here. In general, if you do it for a more general theory, there's some R charge R appearing here. And where is the 2/3? Sorry, going back and forth. This 1/3 is a reflection of that fact. It's R charge divided by 2. And if you compare that with the vector answer, it's 1 here, which looks like as if it's a chiral multiplet with R equal to 2. Right? There's a small subtlety because at that value that this gamma function, when uij is 0, actually has a 0. Okay, you can check that. That comes from here. Okay, you'll see that that has a 0. And certainly that means something is funny, and you can see what is funny. In the physics, there is a 0 mode, which you have to remove, just one single 0 mode for each u that you have to remove. And when you remove that, you get some sort of derivative function, which appears here. This is some standard eta function type of object. It's an infinite product as well. Over all the non-zero modes, this is called the Pochhammer symbol. Okay. Okay, so there it is. So the other expression I wanted to derive is this. The index is this the integral, n-dimensional integral over these eigenphases of this explicit infinite product expression. In this page, I've given you all the definitions. Okay, let me move on. Okay, I'll be very quick now. So the last thing I wanted to say was I just wanted to make some comments on the path integral formalism. Remember that you can always calculate everything in field theory either as a path integral or as a Hamiltonian trace. So I took the Hamiltonian formalism because it's easier, it's more sort of constructive. You can also calculate the same thing using a path integral. And so we expect something like this. It's a supersymmetric path integral, as we said in the very beginning of this lecture, where these where you have to integrate over all fields with periodic boundary conditions on the time circle. You can do this, and you can do this very elegantly using localization methods, where if you, I'm not going to go through this, if you know this, you will remember that the localization answers reduces the path integral to an integral over solutions of the off-shell BPS equations. Okay, and the integrand itself has e to the minus s times the one loop factor. And for our theory, if you actually run that machine, you'll find that in chiral multiplets, the only BPS configurations are when all the chirals are frozen to 0, the field strength is 0 in the vector, and therefore you reduce to an integral over flat gauge connections, which essentially are just holonomies of the gauge fields around the S1. Okay, these are the only flat gauge connections on S1 times S3, and those are precisely our eigenphases that we wrote. Okay, therefore, then when you put it into this localization machine, you'll get an integral over these holonomies, e to the minus action, which turns out to be 0, and then you're left with a one loop determinant, which is precisely these infinite products that I just showed you. Okay, so this is a very, very brief lightning review of how you derive the same answer. There are two subtleties in the path in this formalism. One is this business of anti-periodic versus periodic, but because supersymmetry is guaranteed, there's a killing spinner. Everything goes through with a few modifications. We worked this out in this paper of 2018. You can check that. So the basic localization formalism goes through with very few modifications. Technically, there are some modifications, but philosophically nothing. And the other subtlety is that the one loop determinant in this formalism needs a regulator. There's an infinite product. I said it's a gamma function, but in fact, there's also this kind of 0-point energy. So this thing is called the supersymmetric Casimir energy. And so actually what you get is that the supersymmetric partition function is not exactly equal to the index. There's this term here, which is, so for instance, in two-dimensional conformal field theories, this is like the how you have trace of L0 minus C over 24. It's the analog of that. So C is the Casimir energy in two-dimensional CFTs. The Casimir energy in higher dimensional CFTs is not a physical object. That it can always be absorbed in local counter terms. But there is an object called the supersymmetric Casimir energy, which is like the central charge in 2 dimensions, which cannot be absorbed by local counter terms. And that appears here. This needs to be interpreted in holography. And I'm not going to do that because essentially for the calculation of the black hole entropy, you can just ignore it. Okay, so there's a little bit of an open thing there, which I'm not going to address here. Okay, so you can ask me again about it later. So what have we achieved? The basic point of today is that the AdS CFT correspondence tells you that the supersymmetric path integral on AdS space, to which black holes make a contribution, this was yesterday's lecture, equals precisely the superconformal index of n equal to 4, n equal to 1 superconformal field theories with a simple shift of one of the chemical potentials. And there are two expressions we derived for this index. One is as a unitary matrix model with an action with an infinite number of terms. And the other one is an explicit representation in terms of infinite products. Okay, We'll start by picking up with this expression to calculate some large charge estimates, and on Friday, no, both tomorrow. Sorry, in the fourth lecture, you'll pick up. Tomorrow is Friday. We'll pick up the other representation, the unitary matrix integral, to think about saddles and phases of the theory. Okay, so sorry for running over time. Thank you very much.
Thank you very much. And yeah, so are there any questions?
Yeah, someone raised their hand. Yes, please.
Yes, you can.
I think you already said it in the beginning, but I'm still like somewhat confused because usually like the gravitational path integral is supposed to equal to the partition function of the CFT, not the index. I think you said it in the beginning why in this case it is equal to the index, but maybe I missed it. Can you say it again?
I'll say it. Let me say it in the reverse order now that we understand what the boundary is, and then if you want, I'll say it in the way I said it. Suppose you were given the following problem, that you have a field theory, supersymmetric field theory on S3 times S1, and you're given the observable, which is this superconformal index. It's some Witten index in the problem. Okay. And the question is, what does this mean in the bulk theory? Okay. How do we answer this? Start with the Hamiltonian definition of the index. By the usual rules of quantum field theory, that is a path integral, supersymmetric path integral in the boundary theory. By the basic equation of AdS CFT, that path integral must be a path integral in the bulk. Okay. But it's a supersymmetric path integral. Supersymmetric path integral means that the gravitational fermions, the gravitinians have periodic boundary conditions along the time circle. Okay, that is naively, but the correct way to say that is that it must have supersymmetric boundary conditions around the time circle. Okay, and now the question is simply to that path integral, what contributes in the bulk? Okay, and this was part of the confusion. So in fact, in the old, like initially about 15 years ago, when there was a negative result about the black hole entropy, people had speculated that maybe the black hole does not contribute to the index at all. Because of some fermion zero modes. There were plenty of speculations trying to explain that result. And the answer is that it does contribute if you define it correctly. This is what we saw yesterday. So if you define the supersymmetric path integral properly, namely as a limit, okay, then you can see immediately that the black hole is contributing. Okay? So that's another linear way to say what I said.
Okay, thanks. Yeah. Another question you say here that you will use this to calculate large charge estimates. Is that because the black hole is supposed to dominate the supersymmetric path integral in gravity at large charge? Is that?
No. So yes and no. That's not exactly what I said, but sort of. So there's one question of phases as to what dominates when. That depends on the. So this is an important question. Thanks. And tomorrow I'll pick up on this. So one question is a question of canonical ensemble. So given some sigma and tau, so you plot some phase diagram and put yourself in some point in sigma tau and ask which is the dominant phase. It's like the high temperature and low temperature phase. This we'll do in lecture 4. There's another question about microcanonical degeneracies. This index, if you expand it in a Fourier series, encodes this trace. What is the trace? It says that given some value of the charges, the coefficient of the trace tells you, you're right. Let's say you have only one, suppose sigma equals tau, okay, just for simplicity. Then you have in of tau. It means, so this is trace of -1 to the f times, q to some j to j plus r, okay? So given these states, the question is, what is the black hole? So you expand this, d of n, q to the n. It means that when this charge equals n, let's say 100,000, what is the degeneracy of the black hole? Okay, this doesn't depend on the, sorry, let me back up. The answer to this could depend on which phase you're in if this function is not analytic. So it could be that the function itself depends on the phase of the theory. So it could be that here, there are secretly other dependencies on the phases. That will not be the case for our theory for the supersymmetric index. Okay, there's actually one function which governs the whole phase space, and you see the phase transitions within that function. This we'll see later. And therefore, for the question of the microcanonical degeneracies, it's simply a question, given this function, which we calculated today, right? You just have to calculate
The Laplace transform.
the transform, exactly, the Fourier transform. Okay, divided by, right? And that's all it is. Okay, and that right? That's all we have to do. And this and this, and so when I say large charge estimate, I mean that this charge is large.
Okay. Okay. Thanks.
Thank you. Are there any other questions?
I got one quick question. Can I?
Please, please.
Just about this Casimir energy thing that you were saying. If you do the matching with the microstates counting, is it the index with the Casimir stripped off that you're matching, or is it the full partition function?
Yeah, thank you. So just a second, I'll just open a new page. Let me first remind you of two dimensions. Suppose you have, sorry, for some reason my iPad is acting up. So in two dimensions, so 2D. Okay, the trace Q to the L naught. Okay, but in fact, that's not the right thing to calculate. What you should calculate is this. All right. Now, suppose L naught is quantized. L naught, suppose you have a free field theory, okay, one free boson in two dimensions. What do you get? You get something like this. Okay, so you can call this D of n, or you can call this D of n minus c over 24. It's just a label. Okay. So the answer is that it doesn't matter. Okay, so in other words, if I take I and calculate D of n q to the n, okay, I could put a prefactor here if I want, okay, and it's not going to matter. That's roughly what I meant. Okay, and to answer your question in a less, in a more straightforward way, the answer is I will only discuss this. Okay, there is some issue about the interpretation of this prefactor in holography, what it means in the gravitational theory, which I don't want to discuss because I also don't understand it fully well.
Okay.
But as far as the calculation of the microcanonical degeneracies or the phase structure is concerned, it's going to be insensitive to that.
Okay, thanks a lot.
Thank you. Any more questions?
I have a question. So the fact that you can see the fact that you can see black hole contributions in the index seems really surprising, because for the in the boundary you would expect to have periodic boundary conditions for fermions, and when that extends into the bulk, if you have a contractible time circle, then you shouldn't expect to have fermions. You would normally expect to have fermions in the NS sector existing only for the contractible time circle. What exactly do the new variables do that get over this problem?
Okay, so how have we solved this problem? This is how I began with. So we've solved this both in the boundary and in the bulk. Let me remind you of the two solutions. The main point is that indeed you're right. So you have a contractible time circle. This is the cigar. So you get epsilon to be antiperiodic. But what does it mean for the bulk to be supersymmetric? Okay. So naively, it means that you have some infinite tube. Okay. Yesterday, if you were there in the lecture, we saw how to regulate that problem. The way to regulate it is to give yourself a sort of small temperature, go a little bit away from extremality, and then move towards t equal to 0. But you can do that in a way manifestly preserving supersymmetry. Okay. How do you reconcile these two things that you just said? The fact that epsilon is periodic in a contractible circle is always true. And the way the gravity supersymmetric black hole reconciles that with supersymmetry is the fact that this thing becomes complex, and as a result, you have a background R symmetry gauge field turned on at the boundary here. Okay, maybe let me remind you very quickly of Killing spinor equation. Yes, it is. Okay. You have a Killing, this is yesterday's lecture. You have a Killing spinor equation. Okay. Periodicity and anti-periodicity is not a gauge invariant concept. Right? Momentum is not gauge invariant. Just take basic quantum mechanics of an electron coupled to a magnetic field. The correct momentum is not p mu, it's p mu minus I times a mu. That's what is going on. Okay. So the way the gravity sort of reconciles these two notions is the fact that there is a background gauge field switched on, such that the whole thing is actually supersymmetric, although naively it looks antiperiodic. Okay. Another way to understand the same thing is the fact that that you can start by this loops as if there is no -1 to the f in it, right? So this is what you're calculating, but it's actually secretly exactly the index with a shift of sigma.
I see. Huh.
Okay, so are there any other questions? Otherwise, is there any other? Okay, otherwise we can maybe thank Samir again and